should have learned a little bit about forces in kindergarten. So now we're going to expand what you might have learned earlier on and try to understand these forces that are around us. Now look at that, the girl, she's working on what we call a Chinese yo-yo. Now what is she doing? She's spinning it and she's doing all these tricks, and she's using something that will bring it down, and that's called gravity. So we're going to learn a lot about gravity, because gravity actually controls our lives. It makes us look like we do. It makes us fall down. It makes us try to conquer gravity by developing airplanes and helicopters. So that's one major force on Earth that we will look at. Now, if you look at the other picture on the right, what does that look like? Well, it looks kind of magical. Something, they're attracted to each other. It looks like a little worm. What is this stuff? This is magnetism. So we're going to learn about another force that is part of our life, and that's called electromagnetic forces. And that includes magnets, electricity. And as you know, we use a lot of that. Just turning on the lights, just us getting over to you would not have happened if a scientist did not develop the relationship between electricity and magnetism. This is real important. So we'll learn about push and pull a little, repel and attract, and positive and negative today. So, but let's look at our Earth. Remember, I mentioned that there's many forces. Well, scientists have grouped them into 4 major sources. Weak force, which is at the atomic level. We're not going to deal with that. That has to do with the creation of matter breaking up real quickly. Then we have the strong force in an atom, which all matter is made up of. Inside the atom, when you break it apart, it creates a lot of energy. We're not going to deal with that because that has to do with nuclear bombs and a lot of other stuff that you're not equipped yet to understand. But we are going to learn about gravitational forces due to motion in the universe. Like the picture that you're seeing here, we have the Earth. Hopefully you're familiar with the Earth there, the blue planet, and something's going around the Earth. What is that? Starts with an M. That's the moon. The moon is attracted to the Earth, and as it's going around, it is held by gravitational force. But what's holding us? What is that big ball in the middle? That's the sun. Now the sun, notice it is rotating also, it's moving around, and we are revolving because of the gravitational force. So gravity affects our every being. If we didn't have gravity, we would be out in space far away. Then we are also going to look at electromagnetic forces, a little bit about electricity and magnetism. As you get into the 4th and 5th grade, you will learn more about those kind of forces. But just to be aware, we have forces all around. Now, let's discuss gravity first. Now, what's happening with this drop-down tower? It goes down. I don't know if any of you have been on there yet. Some of you might not be tall enough to be on this one. But as you're going down, it's what we call free fall. They let off the brakes and you fall down. What's pulling you down? Gravity is pulling you down. But as you're pulling down, you feel inside, oh my God, my insides want to come out. That's because they kind of want to. As gravity is accelerating and pulling you down, your organs want to stay at one spot. And so you feel this, oh, this terrible feeling. Some of us like it and some of us don't. But this very, very famous scientist, Sir Isaac Newton, he was an observer of nature. He was a mathematician and a naturalist. And what he tried to do was he tried to look at the world and try to figure out how you can mathematically make equations. And this man was he was known for the apple falling down on his head and understanding gravity, or from that he started to put numbers on it and make rules. And the rules that he has basically 3 rules of gravity. The first one is in blue there. It says every object starts at rest, and then as motion goes on, will go in that direction until something changes. Like just like this drop down force, what stops it? As it gets to the bottom, the bottom, the gears that will hold that one up. Then he came up with that force equals the mass of an object, not the weight, the mass, just how large it is and dense it is, and then how fast it's going. And we're going to introduce a word called acceleration. So force equals mass times acceleration. Sometimes you see that equation all over the place, and it's very, very important on understanding how to do tricks, as we'll go over. Then he came up with another one. For every action, there is an opposite reaction. Like if you hit somebody, what happens? That person falls down. For every action, there's an opposite reaction. If I pick up this ball, if I throw it, the energy from me for every action, there's an opposite reaction going in the other way. So this we're going to see time and time again. Now, let's take a look at these two pictures. What's going on? The teacher in the first one, she has what does she have there? She has like a board, and she has it set up where she goes real fast. And then what happens? The balls don't go with her, but they go down. That's what we call inertia. It's a hidden force that keeps us kind of grounded. Like if we were on Jupiter, would we be standing up? No, we'd be kind of floating around because there's not enough gravity there to get that inertia. Now, what's this other teacher doing? This teacher here is almost like magic, but she's going super, super fast. And then the inertia or the gravity pulls it down, straight down, doesn't give it enough time. You've probably seen the magic trick where somebody will put a dinner and have a cloth underneath it and quickly jerk it out, and then the food just stays there. Don't try that because you have to get good at that in order to do it. But that is based on inertia. It will just go straight down unless another force takes it out. Okay, so now let's look at this. Will these guys go at the same rate? Will it hit the bottom? Look at that. With one book, two books, three books, or four books? Do they all hit the same time? Yeah, they do. Because gravity is affecting it, all the books all in the same direction. Ideally, you've probably heard, and this was one of Sir Isaac Newton's, if you put a feather and a rock in a vacuum, that means no air, will they hit the bottom at the same time? Yes, because gravity affects everything, but there's other forces that either prevent gravity from pulling down, like air can be a force, or so there's other things that come into play. But if everything was idyllic or ideal, then everything would kind of fall at the same rate, but that's not how our world works. Now let's see controlling gravitational forces. Now, if you notice there, what would happen if that man in the red lets the man in the white down? What will happen? The man in the white will fall down because the man in the red is holding him up. So it's like he's countering gravity, but gravity would fall down. Now let's look at these other ways. What's some other ways of allowing gravity to do? So if you look at the next picture, you notice those are, does anybody know what those are? Those are pulleys. Pulleys help us to defy gravity. So if you look at the other picture there, you'll notice a crane. A crane has a pulley on the top, and it's pulling it up. Pulleys can help defy gravity. Without the pull, everything will fall just down. And so there's ways of controlling it. And even as kids, you've learned how to control, just like when you were a baby. Did you know how to walk when you just, like when you were 2 months old? No, because gravity's pulling you down. You have to learn how to use your body to pull yourself up to defy gravity. And that's what our skeleton, if you notice here, Charlie has legs and has a backbone to make us straight. We are designed to defy gravity. If we were on a planet with very little gravity, we would probably look more like an octopus or something slimy without a backbone, because we wouldn't need to stand up straight to defy it. So gravity, again, is with us. Now, look at this here. Can we pick up an elephant just with the pulleys? Again, we're defying gravity, but yes, we can. There's ways, and that's what engineers kind of do. They try to figure out how things move and how gravity affects us and how to counter it. Now, if you look at the other one, though, the three little boys there, they're pulling it up, but they're not sure how to keep it up there. So no matter how much you go down, it will fall down. So we have to understand how to conquer gravity in order to engineer our world. Okay, now I used the word acceleration before. That was the A in that formula, force equals mass times acceleration. Phoebe here is going to show you something about this acceleration. So not only can you design things like pulleys to anti-gravity, there's also another thing that will defy gravity, and we're going to see its motion. Let's see what she's going to do. Phoebe.
Let's do an experiment. Let's see how high we have to put the marble on the ramp to get it to complete the loop. This is level 1. So not quite. Level 2. And level 3.
Now, what happened at level 3, guys? Level 3 actually was able to go around. It had enough force to defy gravity. So acceleration can also defy gravity. Think about a car. When your parents are driving, they're accelerating. And if they didn't accelerate, they would just be at the same speed and really wouldn't move too much. So this whole idea of acceleration and get you going to defy gravity is something that we learned less than probably 150 years ago to really control it. So let's look at this one. Force equals mass times acceleration. Now, what's the difference here? It's the same ramp, but yet which one goes down faster? Are they different? Yes, they are. Some are denser. If you notice, there's the one that is the least dense, the one with the hole in it, goes the slowest. But this is how, and actually, if you like to drive fast cars in races, if you ever look at a race, then you'll notice that some of these cars are engineered to go faster, to accelerate more, and to get more force behind them. So this is just every day we use these principles, and some scientist or engineer designed a lot of the things that we use so we can use it effectively. Now, here's another one. So Phoebe's going to show you what happens. Do you think that ball, if she just put it up on the top, would the ball go around? How can we get that ball to stay up on the top? Let's see. Phoebe?
Make this ball come to this top edge without it falling down. And now, what happens if we stop?
So if we stop that acceleration or we stop this motion, then what happens is it falls down. So with this motion, what it's creating is causing something to go in. And you could see that you have two forces, centripetal, which is going in, and centrifugal, which is going out. You don't have to remember those words, but just to realize that motion will allow something to stay up. You can do this with your with a like a small pail of water, put it halfway, and if you put a rope on it and twirl it around, you'll notice that if you go fast enough, the water will not fall down or not come out of that. That is the same type of force that can hold things upwards. So motion is almost like anti-gravity. Now, you guys have felt this before. You've been on this maybe in a playground. Now notice what's happening. It looks like the ball is going, it looks like it's circular, but it actually isn't. If you look at the diagram before, it's actually going straight, but how we perceive it. So the centrifugal forces really kind of make it look different to our eyes, but everything is this forces on you. Now, if that went faster, would that teacher fall down? Yes, she would, because the force would be so great unless she's holding out. If you notice, she has her legs on those sides there, trying to prevent her from falling. You've ever noticed, I'm sure you've been on one of these before. If you don't hold on, what happens? You go off. Okay, now, how does that apply to our world? Now, this is our world. Now, are things moving on our Earth? Well, let's take a look. Look at the green lines. We're going to take a look at them. Notice they're moving. Now, are they just, those are what we call currents. And what happens is our Earth, because remember, our Earth is rotating around. And as it's rotating around, our ocean, which is not really like land, is like glued to the Earth, if you want to do that, but water is not. And so just the motion of aroundness allows our currents to move. And these currents actually can change our weather. Actually, it creates our weather, believe it or not. It starts with these oceans, and as cold and hot air come up, or cold and hot water, they create different atmospheric pressures. They're moving all around. And this is one of our patterns. So even learning about gravity has a lot to do with weather changes. And over time, it has a lot to do with climate change. As our plates or our land moved around, it created different currents. So this gravity stuff is all around us. We cannot work around life without it. Okay, now let's look at a yo-yo. You guys have probably all looked at yo-yo. If you look at the girl on the right, what is she doing? She's using her hand and going up and down. She's creating a motion, so it's twirling around, and that's enough for it to defy gravity and go up. But look at in space. Now, this astronaut is up in space. Now, if it didn't have a string on it, what would happen? It would just go all over the place. But because it's microgravity up there, you can move it around in a different way. So could that little girl do it? No. Only the astronaut out in space. So there's all these different things that's occurring out, that has to do with our gravity on Earth. Now, let's take a look at how this gravity can shut off. Let's look at this. It's called a Euclid's disk. Now, I know you're going to have to be patient. And although most of you will not have a Euclid's disk, you could do the same thing with a quarter or a dollar, a gold dollar. So let's take a look at what's happening here. Can you predict what's going to happen? Is the motion, is the height of that disk going higher or lower? Why is it going faster? You can hear it. Will it go on forever? Or will it stop? Is it getting smaller? Is it going faster and faster and faster? Is this going to go on forever? Listen. Slower. Faster. Uh-oh, what just happened? Gravity finally overcame. Now, this is the Euclid's disk is very massive. And what it's doing is it kind of wobbles. Now, our Earth wobbles as it rotates. And so that wobbling, well, we're not going to do like Euclid's disk, we're too dense. But there's all these effects. Now, if you notice that glass there is a little what we call concave, and that's what allows it to rotate. But gravity will finally take it over and make it stop. Like I said, you can do this with a quarter. You just spin it and you can watch it. It won't spin forever like I have it up there, unless you are in anti-gravity. Now let's take a look at this forces again. What's happening here? We have a hoop. You got, aha, that goes with Newton's laws. It goes in one motion until another force influences it. So look at this one here. So as it goes, and then he's using it to try to hit that bottle. Okay, so going straight, because the force, if it's not there on the round thing, it just goes out. So this is centrifugal force. Okay, now you probably went, well, how do I use it? Well, can you do a hula hoop? So hula hoops stay up because there's a force as you're going down. You have to use your hips. And if you don't use your hips right, the gravity will take over. But if you make your gravity go upward, if you make your body kind of make the motion upward, it will do the following. And then if you don't do anything, what happens? Gravity will take over. So sometimes if you can't do a hula hoop, you have to pay attention to the motion in your hips to make sure that it's a slightly upward motion, and then you can do a hula hoop. Okay, so there's a trick to even hula hoops because it is gravity that makes it not work. Okay, now here's another one. Have you been on this ride yet? Where it goes so fast, and look at you, look at these kids over there. They're being put to the side. Notice the bottom floor goes down, but yet they don't fall off. Why is that? Because this way, they're having a force going one way and then a force going the other way, and they just are, it's almost like glue. Notice they're having trouble even moving. That this is anti-gravity, and that's how this works. So a lot of these games that you go to a circus or amusement park have to do with anti-gravity. So this is just understanding. Now, remember, these all have to be engineered. You can't make one yourself. You have to figure out how wide it is, how fast it's going in order for this to work. You can't just make your own. Engineers are very much involved in amusement parks. They have to know their stuff. Okay, now also a merry-go-round. If you think about it, it's going around. Why is the mommy and the daddy holding the child? Well, number one, so it don't fall off, but what would be making it go out? Well, remember these forces, one's going down, out, and one's coming in. Now, if she wasn't holding, he would probably, the little child might fall off. Well, probably would, unless he's holding on himself. But that's why you have to hold on. Forces are all around us. Now, why do we go on these rides? Some people go, why would you go on it? Well, it's because it gives you a thrill. And what is that thrill? Because as you're moving, your body, remember that word inertia, wants to just stay in one place. And so as you're moving, you're getting a sensation inside because your organs got to go with it and they're kind of delayed. So this is kind of a neat way of making gravity make you have fun. Okay, now let's look at another one. What do you think this is?
Everybody! I got you guys, I got you! You made it! You made it! You guys did it! You made it! I love you guys! You guys did it! Oh my gosh, you did it!
Now, a roller coaster, simple as that. Remember we went over before, when you turn around, you have to go at the right speed. But as you're going down, this is where you get like a thrill. And that thrill, again, is because your organs want to go straight and your body is forced to go down, and you get this sensation of movement in there. So this whole idea of gravity as part of these. Now, as you know, roller coasters can be very dangerous if they're not engineered and maintained correctly. And if you notice, they are buckled in, because if they weren't, what would happen? Whoop, they would just go out, and that would end that. They would just be flown off because gravity wants to bring you another route. Now let's look at all these. So you got the roller coaster, you have, and it all has to do, we even use it in biology, because as the forces, if you notice on that, the liquid there, that's called the centrifuge. As the liquid is being separated from the solids. And so you can use these principles not only in engineering, but also in biology to extract certain things. So these are important principles to understand how it works. Okay, now this one is kind of cool. Most of you have been on a Ferris wheel. They're pretty benign. You know, they don't really, they go slow enough. But before they had electricity, did they have Ferris wheels? Sure, they sure did. Look at the first one on the left. What are those young men doing? This one isn't run by electricity. It's run by human forces. Notice they're holding on, they're grabbing, and then by their weight. So you can't be a small kid, you have to be bigger, and you're pulling it down, making the Ferris wheel work. Imagine having a job like that. So you would just go there and you're making the Ferris wheel work. So in some areas where there's not electricity, they still have fun. People like this thrill, but I don't think I'd want to be one of those human generators. So, but that's the way it is. Ours go, we can control it with the electricity and with a lot of gears and pulleys. So now let's look at one of these other principles that we've just discussed. For every action, there is an equal reaction. So if we look at the first one, if you pick up one of these balls, this is called a Newton's cradle. If you pick up one, the energy goes through the balls and then comes out, and then the force goes upward. Now let's look at the one on the upper right. If you notice, if you take two, what happens? Two go out on the other side. If you do three, one would transfer, like you're doing right there. If you do four, would it do the same? Yes, it would do the same. Four would go over, so two would transfer. So these are for every action. There is an opposite reaction, but unfortunately, gravity does play a role here, and it will, if we weren't anti-gravity, this would continue forever. But because gravity holds it down by something called friction, that's something you'll learn in high school, that reduces the reaction. Okay, now, so how do you get around from every action reaction? Well, there's these things called springs and gears. And if you ever look at any of the toys, or even if you look at an engine, there's all of these things that try to combat gravity. Some things will make it go faster. Like for instance, when you have a spring, you're saving energy in there. And then when it's released, you have a gear that will kind of control it. So there's all these ways of trying to make things work with gravity. Now, for instance, if you were on the moon or Mars, would a car actually work very well? Or would you go out into space? Think about all these places that we engineer our things for gravity. So when engineers design things for space, they have to think of anti-gravity. So things work a little bit differently. Now, what did I use this? Let's see what Phoebe's going to show us. She's going to summarize the one on the Newton's cradle.
This right here is Newton's cradle. So let's first see what happens when we pull one ball back. Okay, now let's see two. What about three? 4. Okay. What happens if we pull all 5 back?
So there's no transfer of energy in this case. But again, for every action, there is an opposite reaction. Good. Okay, so here we go. Now, so let's go from gravity and let's go into another realm of forces, because gravity isn't the only force that we have to contend with. There's another things that are called electromagnetic waves that create electromagnetic forces. Now, what is that all about? Well, if you notice there, we have radio, microwave, we have infrared, visible wave, that's the rainbow, ultraviolet, X-ray, gamma rays, cosmic rays. Wait a minute, well, they're all different things. Well, no, they actually are all into one force called the electromagnetic forces. And these forces create objects. Once we understand how they work, we can create products. Just like the microwave was only invented about 50 or maybe 40 years ago. And now they're in every home and we don't even think about it. It cooks up things. But before that, all you could use was heat. And so these electromagnetic waves is this interaction of electricity and magnetism. And it creates this movement. Now, so am I telling you that light moves? Yes, I am. Light moves, and it moves very quickly, about 186,000 miles per second. And so movement of these forces can create other things. It could have, you could transform other like physical waves like sound. You can make things cook quicker. You can do radio, you can do TV. There's all these things that you can create. You can look inside your body with an X-ray. You can create these other things. So there's gravity that does things and makes products, and the electromagnetic waves that make products. So now it's electrical force creates a multi-dimensional. So you can do it like gravity was just down to the dense mass, but you can also have electrical forces can create, you can be anywhere. So like when you go out into space, electromagnetic forces still work. It is gravity that doesn't. So now let's look at some of this. Now, even if we have, let's look at electricity. Electricity has to do with something called electrons. Now let's look at matter. Matter is made up of electrons on the outside. That's what this little diagram. And on the inside, which we call the nucleus is made up of things called neutrons and protons. Now, if we take those electrons on the outside, we can make them do work for us. Wow. Well, what's that young boy doing there? He's got and you could do this yourself, you get a balloon, you get your hair, because your hair, we're made up of matter, and we have electrons all around us. So like when we shake or when we rub the balloon on our hair, we're stripping those electrons. And notice what the boy is doing. He then puts the electrons, act kind of like a glue, and you can put this balloon on something that might be positive, because what you're making is electrons are negative. And so these are a way, we've learned how to control this electricity, but at one time we couldn't. Like for instance, lightning is the flow of electrons, and we couldn't control it. What famous scientist and statesman, Benjamin Franklin, started to discover how electricity can be captured and we can do things. Imagine a life without electricity now, but it had to start with observing things that these electrons can do. Now, so can electricity flow through humans? Let's look. Phoebe's going to use Hagos as a guinea pig.
This right here is an alien ball, and they do some pretty weird things. So if I put my finger on the metal part here, and then touch the other end, it goes off. And now we can see if it works with another person. So nothing happens, but if we connect.
So what Phoebe was demonstrating here is that electrons are all around us and we can create a circuit. Now, circuits, you've probably heard of this term before. A circuit is a flow of, electrons can flow through it. Now, do we use those all the time? You better believe it. I could not be working with you right now if we didn't have the flow of electrons to make work. So circuit boards are put in phones, they're all miniaturized, in computers and TVs, and they create work. So controlling this electricity really has helped humans. Now, another, when you can't control it, that's called static. And when you can control it, that would be your series or parallel circuits. So these electricity does play a major part in making products. Now, let's take another look at magnetic forces. Phoebe?
This right here is a bar magnet. So it has a north side and a south side, and the north is marked with a line. So we know this side is the north, and now we can find the north and south poles of other magnets. This is a cow magnet right here, and whereas we bring these two ends together, these are drawn together, meaning this side is the south side of the cow magnet. But if we flip it over, there's a repulsion there. These two sides don't want to stick together, meaning this is the north side. So now we can try another magnet here. Remember, this side is the north, and they attract. So this green face here is the south, but if we flip it over to the black side, again, the magnets don't want to touch. So this is the north face of this magnet. And here we have some other ones. So this purple ring right here is a magnet, and when we take this orange one, they attract. So these two faces are opposites, but if we flip the orange ring over, they repel. It doesn't want to stick because now they're the same poles. And if we move over here to this magnet, we can look at the forces. So right now, none of the magnets are sticking together because they're all balanced. But if we move some closer, they attract.
And we can actually create kind of energy from these forces. Now, when Phoebe used the rings and she tried to push it down, that's where you really could feel these forces. Now, again, magnetic forces can be used in outer space. So this way, if you have metal in your, or magnets in your shoes, you can walk around normally and not float around all the time. But these are, when you start capturing these electromagnetic forces, that's when we've learned how to create things like cars. And this was just at the about the 1900s where we first understood how to make products. And now you don't even, many of your toys are have to do with electromagnetic forces. So very, very important part of our lives. Now let's look at that for magnetics. Look how it's being attracted. So you have north and south just on this little ball here. And if you look on the other, on the left-hand side, you can see these force fields. Force fields, where have you heard that before? Well, our Earth, do we have a north and south? Yeah, we do. We have a North Pole and a South Pole. Does that have anything to do with magnetism? It sure does. As we're going real, real fast and we have metal inside of our Earth, what it's doing is creating these electromagnetic forces. So it goes out the North Pole and into the South Pole, and it acts as a protection. So we didn't know this a long time ago, but this is part of understanding our Earth so that we stay on Earth for a little bit longer. We don't want to breach things that are protecting our human species. But this is all kind of cool. So you might be playing with these as a child, but as those plays, every time you play with something, think, How does it work? Now, and if you want to know how it works, you become a toy scientist. So we're going to read you a little story called The Crazy Toy Scientist. And this will kind of show you what is in your toys. And then when you go home or wherever you are, look at how these things work. And it has something to do with what we've learned today.
The Crazy Toy Scientist by Joyce Bluford, animated by Doris Rea and Hagos Tawaldi, read by Phoebe Chen. There was a crazy toy scientist who wanted to invent cool toys. The toyologist would work day and night to bring fun to girls and boys. To discover how toys work, he would experiment in his lab. It would help decide what toys children would want to grab. First, the scientists had to figure what made toys behave, so the toyologist researched toys that children would want to save. The rubber tree in Central America inspired people 3,500 years ago to mix morning glory juice, creating a toy of bouncing dough. Escaping the Earth's gravity as a rubber ball, it tries to go high in the air, but will only go down and fall. In the 15th century, enlightened scientists would use tin and metal springs to create the first wind-up toys that Da Vinci made for kings. Simple wind-up toys use a spring. Wind them up and let them go. The toy will wiggle and walk and continue to tumble and roll. The cymbal-banging monkey is one of these wind-up toys, was invented in the 1950s, clapping to everyone's joy. In 1913, people were building. Alfred Gilbert invented the erector set, miniature toy building structures to engineer a car, boat, or jet. In 1943, Richard James, a naval engineer, was looking to make instruments stable. He dropped a spring and the slinky was born, walking down his table. The Wheelo, marketed in the 1950s, uses metal that is magnetic, attracts a wheel to the edges, creating energy that is kinetic. The scientists learned chemistry creates materials children shape and mold. Concoctions can develop new toys. To children, it would be like having gold. Principles of mechanics could design toys to move and walk. Gears, springs, and metal, all they need is to talk. Physics explains other toys, including electricity, magnetism, and light. The toyologist just needed to invent a toy for children's delight. The scientist dreamed he invented a new toy, so he found a safe place for it to stay. When the scientist went to sleep, the toy came out to play. The toy used ideas from physics, even chemistry and mechanics. It was able to roll and talk, and had many human antics. The toy was shiny and big. It talked and bounced like a ball. Creating a large mess in the house, there were many a close call. Toys can be fun, but all is not what it seems. Science is behind how toys work, and that is not a dream. The end.
And the point there was that scientists can create these toys, but the whole idea is for you guys to buy them. And so they package them differently, but the science is still there. So a toyologist, which is a real type of scientist, actually creates toys, and usually they're engineers with a good science background. So let's look at some other toys that might use some of these principles.
Why does this toy levitate?
Now, what's making that levitate? Well, magnets. Magnets repel each other. So if you have them in the right area, and if you notice there's a place in there where it can hold, it can levitate. And so you think it's a cool toy, but really it's just magnets. Here's another one. If you weren't sure what that wheel was, do you remember what caused this?
What keeps this wheel from falling off the track?
And hopefully you know it is magnetism, because they're holding it, and then Phoebe's using her hands to go back and forth, so it looks like it's moving. Well, it is moving because the magnets are holding it. Now let's look at another thing.
What do we have here? If we move it around with our hands, we can get it to stack up high like this. And what's making it stand up?
Can you guess? Of course, magnets. Now let's look at this one. Pullback car. What's going here is it's making a spring in there. For every action, opposite reaction. So pulling it back is one action, making the spring, and then letting it go. And so it has no batteries in it. That's what's cool about pullback cars. Okay, now there's this is something that you might want to do. We have a link that explains how to do them, but this is what we call a Jacob's ladder.
This is an old-fashioned Jacob's ladder toy. So let's see how it works. And you can also make your own at home.
Okay. So guys, this is basically what it looks like. If you notice, it looks like it's falling down, but what's pulling it down? This is not magnetism, even though it kind of looks like it. It is gravity. So it's kind of interesting how it you can make one of those. Now, how do helicopters? This is going to go to the activity that we have online that you can do with your class. What do helicopters do? As they're pushing the air down, they kind of go up, and then they twirl it around, and the opposite happens. So it's pushing this general motion, and notice how it's pulling all of this air around. So it works a little bit different than an airplane in that it has vertical motion. Now, what we'd like you to do is to experiment with your own helicopter. Phoebe?
We're going to be doing some paper helicopter experiments. So to make this paper helicopter, you're going to need 4 paper clips, a template from your worksheet, a marker or some colored pencils, and a pair of scissors. So what you want to do is cut along the solid line. So here was a solid line, here was a solid line, and right here I'm going to cut. And then we want to fold along the dotted lines. So for the top, we can fold one this way and the other this way. And at the bottom, we're going to fold along these dotted lines too. And to keep these folds in place, we're just going to pin this up here with a paper clip. Just like that. And you can also decorate these wings however you like. And then once you have your finished product like this, you can bring it up and down, and you can see the wings of the helicopter will flutter.
And the whole idea to have the different, so here we have one right here. And if you notice that we have the paper clip there. So like as you go up like this and let it go, you'll notice that it twirls around. I'll do it again. You can see it coming down. Is there a difference if you put 2, 3, or 4 paper clips. So on the sheet, you can make several of these and see if there's a difference. And remember, this would represent like mass, and we're trying to figure out how it is affected. So just to go over that, scientists experiment and engineers experiment. They come up with an idea and then they try it out. And so want to get you used to how to experiment. Okay, so this concludes our presentation.